So it's just to give you a feel. That's 10 years of work right there on that slide. And it's really been a team of, started out with maybe 4 or 5 people. Now we have about 12 people. And it's just been gradually, increasing our expertise, increasing our breadth, increasing our ability to look at many different kinds of data, and our ability to find ways to communicate what we learn to a user community.
Is question?
Yes?
So when you mean by impact, it's basically the revenue generated, right? But there is an impact on the client side of things. Did you ever find that part of?
We didn't really total that up. That number is for IBM's business impact, and so it's a combination of many things. It can be revenue, it can be cost avoidance, it can be, when we go in and open the door to help sell other software and hardware, that's part of it as well. So we never actually went in and said, for every single customer that worked with us, how much money did they save with our product? It's hard to get those numbers, to be honest. I wouldn't really trust them anyway.
How is any of that calculated, though, especially for the JAM thing, which is an internal effort?
As a company, we're very good about putting numbers on things. I'm not sure anyone's quite as good as IBM at numbering things. And what has to happen for a project like that is someone at a high enough level, vice president or above, has to sign off and say, yes, this really saved this much money. And you have to be sure that it's not double counting with any other project. And then you sort of document it.
Are these actual products like Cognos and SBS, or are these internal projects you use like professional services?
These are, for the most part, what we call assets, research assets that are used by consultants and services folks on engagements.
So you don't deploy them at customer sites necessarily?
Yes, we do. So as part of that service engagement, software will be left behind. And in some cases, we actually have web services that people employ as part of their own offerings.
So you might only bring that into commercial purpose.
Absolutely, we do that as well. And a lot of the stuff, while it doesn't become products, it inspires products. So Cognos does have a set of products coming out in the social media space, which are really, I would say, they're not taking this and implementing it, but they're inspired by it, like the same way that a book might inspire a movie. It's kind of that kind of borrowing of ideas. So over these 10 years, I've realized that there's kind of a set of things that I do every time I have a new problem in the data space. And I started to document those, and recently wrote a paper that tried to kind of formalize this as a real process that anyone could do on any new data set. And so this process, I decided to give it an acronym, and it reminded me somehow of this algebraic operations idea, where you have, please excuse my dear Aunt Sally, parentheses, exponent, multiply, divide, add, subtract. I don't know where that kind of popped into my head, but it was kind of like, you have to do this first, or else that operation will give you the wrong answer. It was that kind of thing in my mind. So that's what I tried to map it to. It's sometimes a little bit strange, but I think it kind of works. So the first step corresponds to parentheses. You have to localize the data first. And the parentheses, I think of that as drawing a parentheses in the text around the thing that's interesting to you. That's why I think of it as a parentheses. So it's both, and by the way, a lot of what I do is textual in nature. I realize I should have mentioned that up front. I do mostly, my analysis is unstructured data, so I think about things from the text perspective. So the first thing to localize is to select the documents that are relevant, but it's also true that not all of the document is interesting, depending on what problem you're trying to solve. So you need a way to both think about the document set as a collection, and also within each document, what paragraph or what sentence or what component of the document is actually going to be relevant to your study. So that's the localization aspect of parentheses. Once you collect your initial set, you'll almost always find that it's part signal and part noise. If there's any way at all that you can go in and explore that data first and remove the noise and keep the signal, do that first, because that's going to really make your analysis so much more powerful. You may have to come back to this step as you get deeper into the steps. You may find what you thought was signal actually turned out to be noise, so go back and expunge it later. So that's the exponent. Multiplication. This actually is about what I call multiple feature spaces. Feature spaces are the things that each document has, each element has, that describe how we want to reason about it. So it's all the different things we collect about each individual data element. In text mining, typically it's the words, it's the phrases, it's that kind of bag of words representation. I think of this as being multiple because there's often not just one way you can do it. You can often find features in many different approaches. You can also use dictionaries. You can use annotations. There's all different ways you can collect information about text, and there's no reason you should limit yourself to just one approach. Also think about it as multiple because it means that every document can have as many features as you want. So it's like many different ways of describing the same entity. Then divide is divide and conquer. And this, I think, is a step that's missed so often in text mining. And I don't know why it's not used so often, but it's the most powerful way to explore text. The idea is that if you're given a collection of thousands of things, it's almost impossible to get your head around that all at once. But if you can break that into components where each component is manageable and each component is homogeneous, then it's pretty easy to understand a fairly short list of things. And so this divide and conquer approach is about building taxonomies that break the data up, but it's doing it in a way that's going to be useful to you for your analysis purposes. The add is the add connection. So once you've got your taxonomies, you've got these groups of things that break the data up, you need to find connections across those different groups. And those connections are what often adds the insight. And finally, the subtract is the uninteresting material. Once you've found a connection, you don't want to have to look at all the different examples of that connection. You want to find a way to prioritize and remove the stuff that's not really telling you anything new, and really focus on the stuff that's interesting. So it's just like algebra, really. So a little bit about some of the techniques that we've designed in these areas. For localization, it's usually about search and query. I've also got a technique called proximal search I'll describe in the next slide, which is really kind of an advanced way of doing search. Snippets are important. Like I said before, the whole document is not always very relevant, especially if it's long documents. You need ways to break it up into snippets. Set operations like intersect and union are very helpful, as well as sampling. So proximal search, think of this as a way to kind of get that initial set going, where it's often very difficult. You have an idea in mind, you have a subject area, but you don't have a query. And the query is the way you're used to getting at data, you know, a certain search term. But it's often very difficult to find that initial query. So what I realized is we can actually have the search engine do the work for us. And the way this works is, I don't know if you can see this text up here at the top, but it's basically this kind of high-level description of how do I remove bitter taste from food? And there's lots of different genes expressions involved and different ways this food company was thinking about this technology. And when I read that text, you know, I could think about immediately off the top of my head like 10 queries I'd like to submit to get all the data that might be relevant. But I wouldn't be sure, you know, whether I got the right query or not, because each query, if I submitted it, might give thousands of results, and how many of those thousands are really most relevant? And did I make the query too narrow or too general? I can add words or subtract words. I can do words within a certain phrase, or I can, you know, do them in a certain distance. So instead, what I do is actually have the proximal search does all that work for me. It takes all that text and breaks it into a set of very long queries that gradually it tries to make more and more general. So the most specific query is like take a whole sentence and put all those words into it as one long proximate query. That usually doesn't return anything. But what you can do is combinatorially start taking words out of that one by one. And if taking one word out doesn't work, take two words out. 2 words doesn't work, take 3 words out. eventually, if your sentence is about 10 words in length, you've got about 1,000 different ways to do that, 2 to the 10th. So it's doable, basically. If you have enough processing power, you can actually submit a paragraph and, you know, in 10, 15 seconds, get all those queries executed. Then the best queries are the ones that have the fewest results, the ones that are the most specific, that return the stuff that's exactly like your input, hopefully. And so what you can do is collect all those best queries, collect all the patents that get returned by the best queries, and then go in and pull the text out and find the text that matches your original input text the closest using a simple cosine similarity. This simple approach, this kind of brute force, doing lots of queries, collecting the result and seeing what works, just tends to work really great. We use this in patent areas, so patent engineers and IBM say they want to see if anyone's infringing on our patents. Well, we have 30,000 patents. It's a huge job to try to search that. But you can actually take a product description, throw that into proximal search, and it'll give you like 10 patents that are really, really close to that idea right away. And the kind of searching used to do would take days to do this, and now it takes just minutes to actually get a set of patents that are very, very on target. So that's an idea of proximal searching. For the tools and techniques around expunging noise, these are things like junk filters, boilerplate detectors, eliminating garbage of all kinds. And you can use both supervised and unsupervised methods to do this. Clustering can help you figure out what's relevant, what's irrelevant, if you have an expert to look at the data. And classifiers can help you to take what you know is good and build a model around that and remove the stuff that you know is not good.